Sam Russick fell in love with architecture while working with the Nature Conservancy in a naturally daylit office building. Sam serves on the board of the Austin Passive House Alliance in Texas as an advocate for building science knowledge in the AEC community. Involved with AIA COTE at the local, state, and national level, she advocates for the protection of finite resources and use of healthy building materials. Her education in archaeology, anthropology, and architecture, paired with her technical knowledge and field experience, positions Sam uniquely to understand the challenges of bringing theory to practice in the built environment. Susan McFadden is a green developer and energy policy expert working on building codes and utility policy to help with climate change mitigation. She has developed the first LEED Platinum office park in Northern Colorado, a net zero residential development in Fort Collins, and serves on the Colorado Utility Consumer Board and the County Planning Commission. She is a Colorado Governor's Fellow and a Fulbright Specialist, which combines her love with travel with giving back to developing nations. We have a number of sponsors who are helping make this happen for us all today and across the whole competition. We appreciate their assistance deeply. Couple logistics here. Caitlin will be showing timing, we'll be keeping track of time, and we'll show backgrounds with when you have 2 minutes left in your presentation and when the time is up. So that will be our notification system. You can see the examples going there. Other than that, please silence your phones when you're presenting and stay muted while you are not presenting. And at some point, we would like to get a group picture, have everybody turn their cameras on and raise the roof, gives a thumbs up, something or other, to have a nice picture to commemorate this with. I believe that's all the logistical information we have. We will begin in 5 minutes. Please let Caitlin or myself know if you have any questions or need any assistance. Welcome everyone to day 2 of the Solar Decathlon semifinals. We'd love to get a picture of all of you. We will would like you all to turn your cameras on and give a good wave to the camera so we can make a big picture to save us all. Give it a few moments for everybody to turn their camera on. We still have a number of people getting set. If you're available, please turn your camera on, even non-presenters, everybody here. It's good. We get a couple more people with cameras on. It's okay, it's just Zoom. You only need to be wearing a shirt. All right, well, we won't delay any longer. Let's everybody give a quick wave and we'll take a picture. Happy Solar Decathlon.
Yay!
All right, thank you very much. We have a combined team today of Hamad bin Khalifa University, Qatar University, Texas A&M at Qatar, and University of Doha for Science and Technology. Please start us off today.
Hello, just give us 1 minute. We're just gonna share our screen now.
Yes. Wonderful. We can see your presentation. Please begin.
Hello, everyone. We are a set of students from Qatar dedicated to designing a sustainable zero energy house for our community. Now, we are very excited to be here today since it is our first time participating. Today, our team will be presenting a home that will combine both culture and innovation in the single family new housing category. Our team is a group of 7 students supported by 4 faculty members. I am Luna, and presenting with me today is Sarah, and she will explain our approach to this challenge.
So we have yes. Can you mute? Okay. Okay. We have realized that in the wake of COVID-19, that the world has changed dramatically. So it has taught us to create physical environments that have profound impact on our well-being. Therefore, we see that we need to provide a living space that prioritizes both comfort and health. We are targeting Qatar's high CO2 emission in our design by creating a house that provides good air quality. We are also looking into the socio-cultural factor of Qatar and its requirement of privacy and segmentation. Our ultimate goal is to provide a resilient home with respect to socio-cultural norms.
As an emergent rapid city, Doha demands innovative solutions that can influence future development and deliver high-performance smart house. Our team took inspiration from Qatar's National Vision 2030. Their goal was to raise the standard of living for their residents while preserving cultural values and practices. Regarding site selection, we see that sustainability isn't just about the building, it's also about the lifestyle that we create as well. Therefore, we chose a site close to a park to promote walkability, near a metro link to encourage public transportation usage, and finally, near vacant lands to inspire future construction.
Since we are dealing with a hot and humid climate with a temperature that can reach as high as 105 Fahrenheit, we are taking in our design advantage of the privilege wind from the northwestern prevailing winds. In our design, our team utilized several architectural features to address these issues, such as maximizing the north elevation to capture the wind as explained, and to maximize daylighting. We also minimized the western elevation to reduce heat gain. We provided a private living space in the courtyard that promotes cooler ventilation. We also employed stack ventilation to capture the northwestern wind. We also incorporated in the design a hydroponic garden that supports the kitchen to create a low-scale self-sufficiency.
In addition, we implemented a wind catcher, which is made of ceramic. So when hot air hits the panel, it condenses. When hot air hits the panel, it condenses, and then it makes it cooler from the other side. So when the wind passes through, it gets cooled down, reducing the heat transfer. It also has a feature of automated panels and air quality sensors. We have also played with the massing of the building and the location of the courtyard to maximize capturing the wind and the ventilation. For the landscape, we implemented xeriscaping and native plants. We also implemented gray water recycling for irrigation. The smart recycling has a quality of monitoring the quality of water. So then it can corrective actions can be taken by the homeowners.
So for material selection, we have used high efficiency insulation, which is rock wool insulation. We have also chosen GFRC as our cladding material, since it has a low embodied environmental impact and it's more resilient to our weather and to corrosion. We are also using a lightweight steel structure for its recyclability and for reducing the costs on the foundation. We are also using triple glazed windows for in our harsh climate. And these are the calculations that we have done for energy consumption and for cooling and heating loads. We put into consideration energy efficient appliances while doing these calculations.
To achieve a net zero energy consumption, a double skin roof was created with solar panels covering only 1/3 of the roof, and the rest is made of reflective GFRC. This allowed air to pass between the two layers, between the two skins, and it further reduces the heat transfer. We are also considering increasing the number of solar panels to achieve not only net zero, but also net positive energy.
Okay, so in our design, we took into consideration a smart living. So we tried to respond to occupants' need by first having them, giving them to control through a smart home application. This application can have settings such as guests coming in. So you have a guest mode, for example, where you'll have your AC automated, your lighting automated, even if you're not at home currently. Another thing is the smart system will track the occupant's behavior. It's a machine learning technology that learns the behavior of occupants and updates itself as the occupant's requirements. The last thing is in this application, we are providing statistics for the awareness of the occupants themselves. They can check where their energy consumption is going up or going down. In this system, we have used the smart thermostat for the AC system. This is also an added advantage in the application itself. Here we can see the interface of the application, where you can control lighting, control the temperature, set your own temperature. You can also, as we said, we're targeting air quality. So we have sensors that look into air pollution. You also can have the water management system connection, where you can see the level of purity of the water and control the water management through that.
Thank you very much.
So in conclusion, our team has designed a house that is not only efficient, but also attractive to the community that we're targeting. Our
That's all the
project
time we have,
will be
unfortunately.
hopefully a shining example of how energy efficient options can be made more accessible and influential to future development. Thank you very much. Here are our appendices and any questions.
Can you go back to your renewable energy slide, your solar and?
Sorry, we couldn't hear you. Can you repeat?
Can you go back to your renewable energy slide with solar and energy production?
Yes, sure.
Very good presentation, by the way.
Yeah, very nice
Thank you.
and drawings. Yeah.
Thank you.
One moment.
One moment, yes. Just give us one moment. All right.
It stopped sharing.
Sorry.
Share. It stopped sharing.
It stopped sharing.
Yeah.
Okay. So how much solar are you using?
So
23 solar panels. 2023 to achieve net zero, but we will probably do more to achieve net positive for the future, for the final stage.
And 450 panels.
450 watts per
450?
panel. Sorry.
Yes.
10 kilowatt.
And so what's the size of the house?
It's 140 square meter. Let me double check how much in square feet that is. We have it in the other slide.
40 square meters?
No.
140 square, which is about 1,500 square feet. About that number.
Right. And can you tell us again what the mechanical system is? I know you mentioned the stack ventilation, the wind catcher for some other ventilation.
Yes, we have also, yeah, we have the wind catcher, the stack ventilation, we have water recycling system, and we
Mhm.
have solar panels implemented, and our application and the sensors that it controls.
Okay. So
Would you like
cooling,
us to elaborate specific parts?
yes. Is there a cooling, a mechanical cooling component?
Yes, we have a centralized AC system, and it's also part of the components that will be controlled by the application.
Here, where we state that we have a smart thermostat, it's a centralized AC system.
So a regular air conditioner, or is it a heat pump, or?
Yes, would Himyan or Habiba like to elaborate on that? It's a central AC, yes. But the type of
It's our regular centralized AC.
So like how many SEER type of system?
I didn't get the question, I'm sorry.
How many SEER would it be? Does it have a SEER rating on it, or is it a heat pump, or? What kind of AC?
I believe it's a C rating.
Yeah, I think it would be a heat pump is, like Sue's saying, is going to be much more efficient. So consider that as your cooling system if it hasn't been worked out yet. I think that paired with your ventilation system is going to be a good match. But yeah, we'd like to see that in holistically with your calculations. It's an important part
Definitely, we
of
will take it in.
the load. Yeah.
It's so interesting to see how you're dealing with your climate
Definitely, we'll incorporate that.
strategies are really exciting to see.
Yeah, and can you talk about the double skin roof? It seems like a nice climate appropriate solution. Is that common in Doha, in the climate?
Yeah.
Yes. So double skin roofs building are implemented. We've seen examples of them, but maybe not specifically here. Now here, since I think we've mentioned before, the energy cost is very low, so people don't really go to an energy efficient approach. So our challenge here was to introduce energy efficient methods and make it look desirable, so that people, even though they're paying near zero for energy here, they would go towards an energy efficient house.
May I add something?
Thank you very much.
Here
Also,
in Qatar,
unfortunately, we don't have any
actually
more time.
are not
That's all the time we have,
Yes.
unfortunately.
Can you
Thank you
add
very much.
can you add data on the cost and marketability in the future?
Yes, sure. I was going to add about a minor detail that we
Thank
don't
you.
pay
We need to
for
let the next university
energy
begin,
here. So
unfortunately.
the government has a has an incentive on.
I'm sorry, we need to let the next university have their
Sure,
time.
thank you very much.
Thank you very much. That was a wonderful presentation.
Nice presentation.
Thank you for listening.
Next, we have the University of Witwatersrand. Please begin preparing. And share your slides. We can see some of the students, but no presentation yet. There we go. Lovely. Witwatersrand, please begin when you're ready.
We're ready whenever you are.
Go ahead.
Can we start? Hello?
Yes, please, go ahead.
Greetings to the jurors and our fellow solar decathletes. We are Team Slot from the University of Witwatersrand, and in today's presentation, we'll be looking at the team's proposed model design as part of the new housing project. Now, quick thanks to our sponsors for providing us with the facilities and supervision, as well as the team, the engineering and built environment for their invaluable efforts. Now, let us look at the current existing states in South Africa. Now, roughly 26% of South Africa's population is currently living in slums. Now, this is largely caused by access of centrifugal economic opportunities, forcing the country's citizens to reside in areas near major landmarks. Amidst the socio-economic inequalities and inadequate access to sustainable housing that is aesthetically pleasing and energy efficient. Now, the team has recognized the existing gaps and therefore seeks to introduce solutions intended to solve the conundrum. Now, the government has introduced the Reconstruction and Development Program post-1994 after apartheid, with modular designs as shown from this slide, that's the top right of the slide. The proposed housing modular designs do not even address the set out contest narrative. Moreover, they do not even fully address the energy efficiency and environmentally friendly development. So the question we should be asking ourselves is, are we really solving the problem? And that what SLOT seeks to investigate. As seen from this slide, this shows a housing type breakdown for informal settlement, which shows a large population of citizens with informal settlement and inadequate housing. Now, let us move to the south side location. Now, Johannesburg has been the selected site with a 4A climate zone, having diurnal temperatures averaging between 36.6 degrees Fahrenheit and 68 degrees Fahrenheit in summers, and nocturnal temperatures in winter averaging at 7.4 degrees Fahrenheit, showing adequate temperature ranges as depicted from the top right of the slide. Now, 3 preliminary sites were selected as the desired site location, and from these 3 preliminary selected sites, Orange Farm was deemed to be a suitable selected site with a proposed or established settlement plan comprised of green spaces as well as community centers. Now, let us zoom into Orange Farm, and here we realize that it's a more gradual landscape, and the team has designed an urban settlement plan. And looking at the right-hand side of the slide, now the desired goals within these established settlement plan is for commuters to live, work, and come together to create a net that has good access to all socio-economic amenities and a settlement that is safe and well connected to its surroundings. Now, from the aforementioned desired goals, in addition to what is depicted on this slide, the team seeks to achieve the 3 pillars of sustainability from the economic, social, and environmental standpoint, whilst upholding the set out contest narratives as proposed by the Solar Decathlon Design Challenge. Now, this is a holistic system that is set out by the team and what the team hopes to achieve when employing this approach as proposed, which brings me to the design strategy.
For a house on the site, the overall construction costs range within the $100,000 bracket for a family home, like the team's estimated project construction costs.
So the overall house has an airflow requirement of about 280 liters per second. This is supplied by a high efficiency VRF system with an outdoor condenser capable of producing up to 34,000 BTUs. The roof design also incorporates sections inclined at 26 degrees, optimized to maximize solar heat gains for the photovoltaic cells on it.
All design works are of rational designs that satisfy the requirements of the National Standard Regulation and Building Standard Act number 103 of the 1976, as amended, a collection of ideas that aim to push the envelope on energy efficiency and greenhouse building spaces. The team decided to employ design approaches that exceed the set codes while maintaining a minimal impact on the environment and economic scale.
Somebody's muted if they're speaking. We cannot hear you.
The movement of the sun. So
Much
since
better.
the selected site is within the southern hemisphere. Now the movement of the sun will dictate the positioning of the house to maximize the solar heat gains. Now the roof inclination, as it said, is at an angle of 26 degrees with an azimuth angle of 0 degrees, and based on the sun movement during winter time, it provides more shading, as is shown from the left-hand side of the slide in winter time, and less shading in summertime. Now, the overall temperature heat gains and house cooling effects are depicted from the right-hand side of this slide. Optimal cooling and the house is achieved with a 7 a.m. to 8 a.m. ranging from a 7 a.m. to an 8 a.m. period, as well as a 7 p.m. to 12 midnight. This is because of that during the day, the use of HVAC system is not taken into consideration due to the use of natural ventilation as a result of the fenestration of the dwelling, which can allow more air intake, and the side with respect to the side movement, which providing more shade, as well as the overhang from the front porch, which will be shown in the architecture aspect, and also the solar tiles from the roof section, which act like photovoltaic cells. Now, the plan for the final submission is that the structural involves the structural system of the dwelling, including the building envelope and the wall design is what will be looked at, as well as the crawl space foundation designed for the dwelling, allowing enough room to store engineering systems such as heat pump, HVAC system, and on-site storage tank. And also a solar tile array design will be looked, which will serve as photovoltaic cells. And lastly, a detailed energy model showing the overall energy efficiency will also be which brings into the contest narratives.
The wall exudes a sense of relief and comfort for the occupants. The material used for the garage door and entrance creates a threshold that highlights the envelope of the house and gives the house a distinct identity. When you look at the floor plan of the house, you see that the open floor layout creates an open feeling for the occupants. The fenestration addresses two key components, namely the HVAC system and the lighting. The large windows utilize a passive cooling system which takes into account the hot, dry climate of Johannesburg and the breeze coming from the northeastern directions. The location of the photovoltaic heat maximizes heat gains whilst keeping the aesthetic of the building in mind. Because of the climate and the terrain, there was no need to implement stringent disaster resistance measures. The open layout creates a fluid linkage system between the indoor and outdoor space. On the outside of the house, we made use of many trees to provide passive cooling. The trees also tie in with biophilic design to invoke a greater positive connection to nature.
In a goal to reduce electric consumption, we incorporated the biogas digester. The biogas digester collects wastewater from the cluster of houses which undergoes anaerobic respiration to produce gas. The biogas mainly consumes methane, carbon dioxide, and a little of water vapor. Enzymes are added to increase production of the gas. The water enters in through the left side into the dome-shaped chamber where it is stored for anaerobic respiration to take place. When the gas is produced, it occupies the volume above the water, pushing the water down to leave it to the left side. When the gas is being collected, the gas valve is opened and the water waste pushes out the gas in trying to maintain the water levels.
Now, other engineering systems that have been looked at is the rainwater harvesting system, as well as the permeable pavement system. Now, as depicted from this slide, a section of the roof will serve as a catchment system intended to direct water to an on-site storage tank, taking a tank filter screen into account. Now, looking at the permeable pavement section, is that the team has looked at a section from the exterior aspect of the house to serve as a permeable pavement system where water will be filtered through the pavement and will be drawn in and stored from a localized tank, and whilst leaving the remnants. Now, based on the
Thank you. That's all the time we have.
Harvested rainwater was found to to be roughly 3,700 gallons per year, and the storage capacity was estimated to be at least 530 gallons. And therefore, the design tank filter screen was roughly 20 inches in this case.
All right, can we hear from the jurors now? Thank you for that presentation.
Great, thank you all.
Would love to have had more time.
Yeah.
Thank you very much.
Can you explain a little bit more about this? You said they're using solar tiles versus solar panels. Is that correct?
Sir, can you please repeat the question?
Yeah. Can you explain a little bit more? Are you using solar tiles versus solar panels? Is that correct?
No, we're using solar tiles, yes, not solar panels. For the overall roof section, more like roof shingles, will be replaced by solar tile, and they will act as photovoltaics.
Okay, and what influenced that choice? I'm just curious. Was it performance of the tile versus the panel?
Yes. So we've looked at the output of the solar panels and the solar tiles, and we found that the solar tiles do have a greater output because then they run for longer than the solar panels, the conventional solar panels. And then we also save on material costs. So apart from using roof shingles, we're going to be installing the solar tiles instead.
Great, thank you.
Do you have any cost or marketing data on this, and why just one bedroom? And I love the architecture, it's very fun.
And you said it was $100,000, is that correct, for the construction cost?
Yes, it's about just over 100,000.
Okay.
And how would that compare to a similar, I guess, house in the area?
So basically, it is standard procedure within the area for families to be around four to five. If space is utilized effectively and we utilize innovative methods, one bedroom will suffice, provided that there's enough space.
And cost-wise, does that just comparison in the market, is $100,000 for the size of the home comparable, or is that much more, much less?
It is a suitable price, considering that we plan to utilize this design at a large scale. If we're working together with the government, there's going to be limited funding from their side. So we had to implement measures that's going to let us utilize efficient architecture with a specific budget.
So to elude from what my colleague has said, if you look at the number of residential properties by market, you would notice that from 2008 ranging from 2019, since now our overall cost is within the $100,000 to $200,000 bracket, you'd notice that there's an increase in the number of residential properties by market, showing a vast increase in affordability when it comes to people who are interested in the types of modular designs we intend to propose. Therefore, which induces a potential buy-in and makes our house more of a selling within the housing market.
And why 10 kilowatts for 900 square feet? That seems like a huge amount of solar.
Yes, thank you.
So-
We need to be very brief, please.
Oh, okay. I was about to take the 10 kilowatt question. So the 10 kilowatts was actually explaining the amount of power for the HVAC system. So this was something that was analyzed, and then with the estimations, although the estimations were quite rough because this is still very early on and then materials are still going to be optimized. This is what, this is the data that we got saying that we need to have a system such as this.
Thank you. We need to let the next team begin their presentation.
Thank you. Good project.
Okay, thank you so much.
Thank you very much.
Looks wonderful. Next, we have Loughborough University. I hope I'm pronouncing that right.
That's Loughborough.
Loughborough. Please begin when you are ready. There, we can see your presentation.
Okay. Yeah. Hi, everyone. Good evening from the UK. Welcome to our presentation about our smart climate-proof house in the new housing division. So today I'll take you through the team members, project summary, goals, climate study, target market, and how we achieved net zero. So the team consists of Professor Maru, who is our faculty lead, myself, Joshua, the team lead, and my team members are Dimitris, Shafiq, Neda, and Casper. The most common house type in the UK is the semi-detached house, with around 7 million of these properties in the UK. There are approximately 38,000 houses newly built in the UK every year. UK, as every other nation, is trying to combat the climate change. Also, we should not forget the fact that we are in the post-pandemic era where remote and hybrid working are here to stay. And as per research, it is expected to increase in the coming years. Therefore, Loughborough Berg team aims to propose a smart, climate-proof, semi-detached house design, which can also suit the current remote and hybrid working in the UK. Our chosen location is Loughborough. It is located in the Midlands region of the UK. Next, we will look into the climate. UK has a temperate climate. For this study, we use the International Weather for Energy calculation as the current weather file, and the future weather file we used is the DSY 2050. From the top figure, you can see the summer times of temperatures of DSY are higher than the IWAC data. The maximum summer temperatures are around 35 degrees Celsius, which is 95 degrees Fahrenheit, and winter temperatures are around -8 degrees, which is 17.6 Fahrenheit. Also, from the bottom one, the horizontal infrared radiation intensity is higher in the DSY data. The relative humidity is the same for the both scenarios, ranging from 25% to a maximum of 100%. The below figure shows the wind speed comparison for the weather data with a higher wind speed of about 15 meters per second during winter time. So let's look at the target market. So our target market is the middle class family in the UK. The UK national average gross monthly salary is around $3,200 per month. The take-home salary is around $2,600 per month. So the mortgage is approximately 4 times the national gross salary, and they need to give a 15% deposit. So overall amount that the person in a middle class family can afford is around $207,000. So for 2 houses, it's around $414,000 because the semi-detached has 2 units. Overall, the expense for the house that we are planning to create is around $352,000. So that's the target amount that we set initially. So the main project goal are to achieve net zero energy and carbon, use low embodied carbon materials, and increase the productivity and well-being of a home office by providing good indoor environmental quality. To achieve the goals, our design strategy is first, reduce the demand, second, improve efficiency, and third, to use renewables. So this is the typical layout and design of the 3-bedroom semi-detached house in the UK. The building size is 3 stories with around 2,982 square feet of area. We didn't make any changes to the layout as we plan to keep it the same way, but try to create a smart climate-proof house using optimization. This will set as an example for the future project. We have the living room and kitchen in the ground floor. The second floor is comprised of the bedrooms, and the top floor has the home office so that it gets more daylighting in the office space. We approached the problem as a design optimization study. The objective was to minimize the heating load and cooling load. The design variables were window to wall ratio, insulation for external wall and roof, double or triple glazed window, and the building orientations. We used the NSGA2 genetic algorithm as an optimizer. We got the Pareto friend with optimal values, and we chose the optimal one for our study based on the cost of the construction. So now let's look at the optimal values and the R and U values of the building envelope. So the main insulation material we used for the house is the hempcrete block. It is 100% natural material that provides good insulation and fire protection, and it is eco-friendly with a low embodied carbon. The external wall has the hempcrete block and the corrugated hem sheet, which gives an overall R value of 5.5 and U value of 0.18. The roof has an R value of 9.6 and a U value of 0.34. The ground floor has an R value of 5 and a U value of 0.2. The windows are triple glazed with an R value of 1.7 and a U value of 0.68. The window to wall ratio is 40 to 50%, and the optimal orientation is 175 degrees. So in order to provide shading for the windows, they were recessed by 200 mm. This helps us to reduce the summer heat gains in the building. The design optimization helps us to reduce the energy demand. So next is to improve the energy efficiency. So for lighting, we use the LED lights, and for HVAC system, we mainly use the MVHR coupled with the heat pump. So this is an air to water heat pump linked to the MVHR to provide heating and cooling for the house. The ambient air passes through the MVHR and then it uses a heater cooler before entering the room. This ensures the air entering the room is the correct temperature, which helps to avoid occupant discomfort. Also, minimum fresh air of 10 liters per second per person is provided using the fresh air intake in the MVHR. The heat pump is then linked with the heat batteries to provide domestic hot water for the house. So this fully eliminates the use of natural gas in the house. The overall design strategy helps us to reduce the total energy use intensity to 18.18 kBTU per feet square per year, which is 57 kilowatt hour per meter square per year in SI units. In the heating demand is around 1.58 kBTU per feet square per year, and the cooling demand is around 0.024 kBTU per feet square per year. So this is for the IWEC current weather data and before adding any renewables to the house. Next, we look into adding renewables, which is the PV panels to the house. We ran an optimization study to find the optimal angle based on the current and future weather data. The optimal tilt angle for the maximum electricity production was 40 degrees. The PV panels were connected to the inverter batteries, and they were stored as a DC and converted to AC. So this graph shows the maximum AC current available to use in the house after all the losses. So after incorporating the PV into the calculation, our house net EUI reduced to minus 9.1 kBTU per feet square per year, which is minus 28.7 kilowatt hour per meter square per year, creating a surplus energy. So we compare the EUI for the same house for current and future climate. The EUI before renewables were the same for the houses. There was a bit of increase in the cooling load and decrease in the heating load in the future weather file, but they didn't affect the overall EUI of the house. We calculated the embodied carbon of the material, and since we used most eco-friendly, 100% recyclable and carbon negative materials, we had a very low embodied carbon for the house. We reduced the EUI of the house. So what about the comfort? We did the overheating analysis and found 0 hours of occupied house going about 26 degrees Celsius. Also, we ran the daylighting analysis and we achieved a good daylighting in all the areas, including the office space in the attic. So the national average utility bills for two units in the semi-detached house is around $500 per month. But our smart climate-proof house maximum utility bill for the 2 units per month is around $165, which is $82.5 per unit per month. Also, the capital cost for a house for family to buy the house is around $150,000 per unit. So overall house for the semi-detached to create the 2 semi-detached unit is $300,000, which is less than what we have calculated. This is very affordable for the target market and an eco-friendly house as well. Therefore, the smart house is a net positive energy home with a good indoor environmental quality and can achieve A+ rating in the UK Energy Performance Certification. Thank you.
Thank you very much. Jurors, now it's your turn.
Do you know what the HERS ratings are before, pre and post PV?
So I mean, I think the HERS rating is something like for the we have to look into which location in the US, because it when we looked into the free tool that you said in the Solar Decathlon website, we had to look into that, and we used the Tennessee climate, and it showed us like HERS of 5 before using renewables. So it's the UI is basically before renewables is 18.18 kBTU per feet square per year.
I've never heard of a house 5 HERS 5 before PV. That's fabulous.
Yeah, that's why we went into the design optimization to optimize window to wall ratio, to look into the U values for the external and roof, so that it gives us an optimal value. And also we looked at mainly reducing the heating and cooling loads. So we looked into that. That's the objective that we had. And the design variables were window to wall ratio ranging from 20 to 80, and insulation ranging from 0.1 till 0.5 U value, and then windows for double and triple glazed, and then building orientation set to 0 to 355 for every 5-degree angle. So that was a huge optimization run, but then we got the optimal values. And we chose the value based on the optimal cost that we had, because we set a target cost for the overall house. So that's where we used that.
Could you go back to your envelope R values really quick?
Yeah.
Okay, thank you. Gotcha. Meters squared. External wall.
So the external wall is R value of 5.5, which is the U value of 0.18. The roof has an R value of 2.96. The U value is 0.34. The ground floor has an R value of 5 and the U value of 0.2. The internal wall has an R value of 0.67. And the windows are triple glazed with an R value of 1.47. And the U value is 0.68.
You need to update those to our units. We don't understand them, but
So it's okay. Yeah, sure.
Yeah, I was just trying to do the conversion, but just wanted to look at that real quick again. And hempcrete, is that yeah, can you explain that choice?
So the hempcrete is like a material that you can grow in the forms. So the hempcrete is actually natural, and also it's recyclable, and it has a fire protection as well. So it has a good insulation rating as well. So it's something like the EPS and other insulations, but then it's naturally grown. So in the UK, mostly in the passive houses, they are using the hempcrete materials.
And then just a quick, so your target, family was a middle-class family, and you had mentioned a $352,000.
Yeah, so for a single family, it's $207,000, so that they can afford. So it's a semi-detached house. So there will be 2 units in the house. So that's 1 unit and 1 unit. So for 2 houses, it's around $414,000. That's the affordability range, and we set a target of making it affordable for like $352,000. But the one that we created is around $350,000. Sorry, $300,000.
This is an exceptional project. You did super fine details and analysis. The only thing I would say is, what's the marginal benefit of those triple pane windows is the one thing I would look at, but you already got the cost under 300. So that would be the only thing I would look at.
Thank you very much. It's a great presentation.
Thank you.
Yeah, thank you.
Let's move on to the National School of Architecture and Urban Planning and National Engineering at the School of Monastir. And then we will have a short break after they are completed with their presentation.
This is our Tunisia friends, right?
Yes. Hopefully we have some on the call today.
Hello. Do you hear us?
Yes, we do.
Do you hear us?
Yes, we can hear you.
Presenting minutes.
There we
Can
go.
you see our
We can see your
presentation?
screen. Yeah. Can you put it into presentation mode?
Yes,
Wonderful.
we already did. Okay.
Begin when you're ready.
Okay, so hello everyone. We will be presenting our new housing project Serenity Day. We are Durability, a team of 7 architecture students working on the design of a new house in collaboration with our design partner Tasmim Office and the architect Ben Hadid and our 4 industry partners. We wanted to address the issue of ecological and passive buildings that are very underdeveloped and almost absent, especially in the housing sector in Tunisia. Our project is located in Gamart, a northern suburb in Tunis, situated on the Mediterranean coast. It's a residential area, mainly reserved for individual housing. Our site has a 16-foot drop slope with an open and direct view towards the sea and the forest. So our goals are to reinterpret the traditional patio and reintroduce it in modern designs despite the inconvenient current urban legislations, minimize the cost of construction and energy consumption, innovate by using building materials that have been limited to industrial and office buildings so far, thus to minimize costs and maximize insulation. To make this achievable, we have set design goals related to our cultural heritage by the reinterpretation of, firstly, the patio, which is a traditional architectural element in Tunisian architecture. The patio is traditionally bounded by walls on all 4 sides and is an open-air central element, a must-cross area to access any of the house's areas. It provides daylight and natural ventilation and is also needed for gatherings and some house chores. We also implemented the traditional water harvesting system called Mejel, a domestic cistern to collect rainwater to overcome the drinking water crisis developing in Tunisia. We also drew inspiration from the traditional musharabieh. It's an open work partition used to catch wind and for passive cooling, to create a laminated partition instead that also filters sunlight and preserves privacy. The goal is to see and not be seen. We had an unfavorable setting for the building's orientation because the views to the sea and the forest are to the north, while the best orientation in Tunisia is to the east and south, which is facing the neighboring house in this case. So we conducted several solar simulations on various forms to maximize natural light and work in favor of the scenic views. It resulted in an L-shaped design with big openings toward the northeast and northwest and a refreshing patio for hot sunny days. The south side had small openings. The materials used for the envelope were chosen according to their thermal insulation index. Comparative analysis between locally made materials was conducted, taking into consideration the higher-end family house market. We also worked on reduced maintenance through our choice of exterior painting. The average cost for a typical non-ecological house in Tunisia is $645 for square meter, and the design partner's goal is to build a performing ecological house without exceeding this amount of money. To achieve this, we have decided to introduce envelope materials that are usually used in offices and industrial buildings to the housing market. We have also chosen materials and surface treatments that will reduce long-term maintenance. Gamart has a Mediterranean climate characterized by a hot and humid summer from being close to the sea and cool and relatively wet winters. The average annual rainfall is 361 millimeters, which corresponds to a semi-arid climate. Regulation-wise, The sustainability and energy efficiency framework is underdeveloped, especially for the residential sector. The regulatory framework includes labeling and incentives such as EcoBad label for the design of highly efficient buildings, or the Promo ISOL program to promote roof thermal insulation in new and existing buildings. We will start working on the detailed technical and energy aspects starting from next week, now that the sketch is drafted. When all the envelope material choices are finalized, we will dive more into energy, HVAC, and electrical aspects with the engineers in our team. For the architectural contest, the house is for a family of 4 who demanded an office area for one of the parents and extra rooms for guests and a housekeeper. There are 2 entries to the house from both roads that are on different levels. The entry from the dead-end street provides access to the office area on the 1st floor, while the entry from the main street allows access to the main floor, which is the 2nd floor. 1st floor is more of a service floor with the housekeeper's private space and the office area. To the left are the stairs connected to the 2nd floor, which is the main floor. We enter into an open space divided in sub-areas, hall, living, and dining spaces, all visually connected to the central patio. Our project's patio maintains the functionality of the traditional patio, but it is only bounded on 3 sides with glass partitions. It is no longer the must-cross area to access spaces around it. Flow is organized around it, all while keeping independent access to the patio from every space. Our patio brings in a controlled amount of natural light inside the spaces and provides effective cross ventilation. The 3rd floor is more like the private floor with a very large terrace open on the patio and facing towards the sea and forest views for fresh evenings outside. Privacy is also kept with a significantly reduced size of the openings in the walls facing the street and neighbor. The reinterpretation of the musharabiyah on the main facade filters out sunlight. For engineering, we have introduced our former plans, but due to lack of viable alternatives, we are currently opting for the standard post and beam construction with hollow concrete slabs. This is the composition of our roof slabs and walls. We have reduced the use of concrete thanks to a simple design that limits concrete intensive features consisting of polyurethane insulation foam. The total budget is estimated to be $210,000, including design, construction, and PV solar installation, shown here as a percentage of the construction cost. Due to global warming, Tunisia has recorded highest temperature records the past few years, reaching 45 degrees Celsius, equal to 113 Fahrenheit, and data also points to a reduced rainfall rate. So we worked on an optimal building orientation to minimize energy consumption, and garden plants that are adapted to arid and semi-arid climate. It requires low maintenance and reduced watering, turning dew into potable water and a great water recycling system that is extremely rare in Tunisia. We compared materials life cycle to the standard Tunisian double brick walls with a cellular concrete isoblock wall, and we found that isoblock emits significantly less greenhouse gas compared to the baked brick due to cold mixing and natural air drying. This slide here highlights the shading elements and reduced window sizes on the southeast to reduce heat gains and sun exposure, the patios, cross ventilation, and the musharabiyah for natural ventilation, shading, and sun control. The photovoltaic panels will offset lighting and air conditioning needs. We have checked the annual average of energy consumption in a typical Tunisian house of the same area. It's more or less around 7,300 kilowatt hour per year, and we try to fulfill the need by installing a total of 15 panels that will produce over 6,700 kilowatt hour a year. We currently have an ongoing study about the feasibility of a geothermal system, specifically a Canadian well solution for both heating and cooling for a quiet, energy efficient, and non-polluting ventilation system. We opted for the isoblock because of its insulation, acoustic, and thermal performance, which allows us to eliminate thermal bridges. We also used plaster boards for inside walls to reduce indoor humidity and improve air quality. So the house is designed to encourage residents to benefit the most from the terraces and patio and reconnect with the outdoors and enjoy the scenic views of the Gamard Bay and forest. Thank you.
Thank you very much. Jurors.
You want to go, Sam? Wonderful architecture, very beautiful, and you did a huge amount of work on the mechanical.
Thank you so much.
So your write-up says it's $600 a square feet, but it's $600 a square meter. So it's $66 a square foot, which makes a lot more sense.
Yeah, maybe. Yeah.
That would be, yeah, very expensive, but that makes more sense, definitely. Yeah, so I think the kind of concept around the traditional patio is really nice. And you mentioned the commercial materials, kind of bringing that into the residential space. And just for clarification, is that because of, yeah, can you explain that choice again? It'll be more expensive, but just wanting to understand better.
Usually
The commercial, yeah.
they use bricks to build a house, so they don't use concrete or other materials. They use it mostly in commercial buildings. So that's why. But it got
more expensive.
it's more expensive, and the greenhouse. So the greenhouse sector, like Tunisians usually don't opt for ecological. First of all, because it's just not a common mindset. And secondly, it's more expensive. It's really expensive to try to build ecologically. So everyone just opts for the baked brick, which is the cheapest and most easiest solution. So we tried to implement industrial materials like the isoblock brick. It's more ecological, and it's more economic, and it got a low impact on the environment than the usual brick.
Great, thank you.
Do you know the HERS ratings before and after on this, or it's something you don't use?
Do we know what, excuse me? Usually we don't use it actually, but we did a little research, and without the renewable energy, it's 73.5 kilo BTU per feet square per year, and with the renewable, it's 49.
Okay, so for this project, you have to get to a HERS rating of 45 before PV, and then below 0 after PV. So if you were to go on to the finals, you'd have to optimize it for those two criteria.
Yes, actually, we're going to start working with engineers, so we'll try and reduce the HERS score the maximum we can.
Okay.
And I think looking at your window to wall ratio, I think you're just looking at the design right now, it looks pretty good, but just maybe optimizing for certain orientations and looking at potential for shading, given that you have the kind of the carved out traditional patio. It's going to be a nice light well there, but that might be some place to start.
Yeah.
Super great architecture, and using the site, really maximizing the value of the views and everything on the site is really fun.
Thank you. Thank you.
Any other questions from the jurors? Wonderful. If not, then we will take a 10-minute break, and our next presentation will begin at 11:20.
Thank you.
Thank you very much.
Thank
for the presentation. Hello once again. Team from Central Florida. Are you around? Can you begin preparing your presentation?
Yes, we are preparing. Thank you.
Wonderful. We can see your presentation. That looks great. Let's wait a minute or two until our jurors return, and you can go as soon as they're ready.
Okay, just let me know.
Welcome back, jurors. Are you ready for the next presentation?
Yep.
Wonderful. All right. Begin when you're ready.
Hello, we are the Night Lights, and we represent the University of Central Florida. Our team consists of 5 mechanical engineering students pursuing our undergraduate degrees under the guidance of our faculty advisor, Dr. Parahovnik. Our presentation is broken into 9 parts as shown. Our 3D model displayed here was created using Chief Architect.
Our new housing design is located at 13232 105th Place in Live Oak, Florida. This location provides an off-grid type feeling, also being 15 minutes south of the downtown Live Oak area, which includes the grocery stores, restaurants, and other shopping locations. But one benefit for a family in this location is that the elementary school, the middle and high school are all within a 7-mile, about 15-minute radius. Our location is a climate zone 2A, which is a warm, humid region. The average temperature in this area is about 92 to 73 in the summer and 65 to 42 in the winter. So a unique challenge presented by our location. It deals with hurricanes, so resilience was a primary consideration for our design. Our house is designed around a four-person family, 2 adults, 2 children, with an extra bedroom for family members or guests to have over. For the type of world we live in right now, we really wanted to hit on the work from home environment, providing an office space large enough for 2 people, as well as an ample amount of space in the master bedroom in case you want to be separate. And our lot is about 5 acres, allowing for sufficient opportunities in recreation, small scale farming, and space to add more facilities if needed.
To maximize energy efficiency, our proposed design will utilize a long east-west axis build with the front of the house facing north. Due to Florida's warm climate, careful consideration regarding house orientation is a key factor in passive solar design. To further offset the carbon footprint of the low carbon concrete for the ICF wall structure, EIF stucco cladding for the exterior wall and magnesium oxide drywall for the interior wall will be utilized within the building envelope.
Building codes set forth by the state of Florida and the International Code Council were considered throughout the design process. Our proposed design's main goal was not only to meet the standard requirements, but also to exceed each requirements for each component stated. Our team was able to achieve this goal through extensive research and ensuring that each material chosen will contribute to the building's overall energy efficiency.
For our HVAC system, we opted for a closed-loop horizontal geothermal heat pump due to its high efficiency and sufficient land area for installation. This model has an energy efficiency rating of 34.3, more than 2 times higher than the Energy Star Tier 3 requirement. It also comes with a domestic hot water generation system, which uses waste heat to meet water heating needs. This system eliminates the need for a standalone water heater unit entirely.
Our design will integrate advanced technological systems that will increase comfortability and overall efficiency. A motion-activated security system, smart temperature control, and auto-dimming LED lights will be utilized throughout the home. Key factors such as ease of accessibility, security, and affordability were considered when finalizing these decisions. Altogether, these systems can be connected through a smart home device and allow the occupants to control their home settings, either manually or automatically.
To make a baseline for our design, we ran heating and cooling load calculations against the code compliant parameters, and the results show that our design is over 15,000 BTUs per hour less, about 33% more efficient than a code compliant home. The software used was Trace 700. It's made by the manufacturer Train. And to do this, the parameters for these calculations involve the exterior wall, roof and window dimensions combined with their respective U factors. The software uses the ASHRAE's heating and cooling degree days and local climate information to calculate the BTU per hour and offer a HVAC design mode.
As Florida is located near the equator, it comes at no surprise that its main source of renewable energy is solar power generation. By adding solar panels to the roof at an optimal 30-degree angle, the solar panels can generate on average 13,199 kilowatt hours per year. SunPower's X-Series residential solar panels maintain an efficiency greater than 22% and have a nominal power rating of 360 watts per panel. When using 25 solar panels, we can reasonably generate enough power to meet the house's estimated system requirements.
This design takes advantage of government grants, subsidies, and credits totaling in $4,000 and $740 in savings. ICF blocks and solar energy generation have the biggest precedence within this design by building a structurally sound home with designs that cut consumer costs for energy utilization. With an ICF framework, the concrete blocks offset the labor and material costs in comparison to a traditional home from $16 per square foot to $7.09 per square foot, while also lowering the cycle time for wall construction down to around 1 month.
While solar panels can be costly investments, they can over time pay for themselves. On average, a solar generation system selected will produce in excess of 2,895 kilowatt hours per year, which will in turn allow the homeowners to recoup the $25,000 spent on the system in as little as 20 years. The total design cost includes contractor expenses and the indirect building costs, such as building permits, applying utility connections, and construction specifications.
Measures that will be implemented to reduce the embodied environmental impacts include reusing materials to reduce waste, using Energy Star rated appliances which use less energy, and choosing low carbon materials. With these implementations, our team aims to reduce the amount of greenhouse gas emissions with our proposed design.
Using the Ecotrope Radar software, our design was given a HERS score of 35 without PV generation, which is over 22% lower than the specified maximum of 45. With PV generation, our design has a HERS score of -11, firmly qualifying it as a positive energy home. This results in an estimated annual energy bill savings of $1,327. Going forward, the duct and piping network still needs to be finalized, and we have also been looking into a way to reclaim rainwater for use in certain fixtures. Some details still need to be added to the computer model, and our cost analysis will be refined with more specific data. After all of that is complete, we will continue adjusting parameters of our design to further reduce our HERS score, as well as exploring methods to reduce costs without compromising the effectiveness of the design. This concludes our presentation. Thank you.
Thank you very much. Let's go to the jurors.
Great, thank you. That was a thorough presentation, lots of detail. Maybe Sue, I can kick it off. So just a quick question about low carbon materials. You had mentioned low carbon concrete. So what was the which strategy are you using for low carbon concrete, or what's your mix like?
I don't think we specified a specific mix for the low carbon concrete, but one of the downsides of the ICF walls is while they are very resilient, concrete in general is not a super eco-friendly material. So we just decided that we would look into avenues for reducing the carbon emissions based off that to offset that cost.
Okay, great, thank you.
My question is on the overgeneration. I mean, we all like to be net positive for sure and think we're doing something good, but the grid actually does have value. So you spent 25,000 on your 9 kilowatt system or something, but you overproduced by a HERS of -11. If you went to a HERS of 0, that would probably save you 3 or 4 kilowatts of solar. What's the net metering? What's the logic for overproducing? Is there a net metering reason with the utility to do that?
Not specifically, we just wanted to make sure that we could meet our house's energy demands at any point in the year. But we can take having like a HERS score closer to 0, we can take that into consideration for the final submission.
Yeah, I think based on our calculations right now, the solar panel system would pay for itself in about 20 years with the tax credits we'd be getting back for putting energy back into the grid.
So it would pay back much faster if you right-sized it. And are you looking at any EV? Does the DOE 0 and the IEC 2021 require EV ready? Anybody know?
I think you're right, Sue. Yeah, just electric vehicle. Yeah.
Charging, or at least the plug to the garage, or the wiring.
Yeah, I don't think we opted, our person who was going to answer that question can't unmute for some reason. We didn't opt for an EV system. I guess we didn't realize that was a requirement, but considering we're over generating with the solar panels, I guess when we look into that, maybe we will be closer to a HERS score of 0 once that's taken into consideration.
Yeah, or you can say that, or you're putting it in a hot tub or something.
Just a question about the climate. You mentioned hurricane. You'll be in hurricane. You are in a hurricane climate. Can you reiterate or just tell us a little bit more about some of the resilient strategies for high winds?
So that's definitely a reason we went with the concrete walls with the ICF. The concrete walls provide a great resilience to the high level winds that come with the hurricanes.
And how about your windows? Yeah.
So for the windows, we're using a horizontal slider double pane with low emissivity. So when I was doing research, it was kind of suited best for our climate, and it was sorry, it was also more suitable for the hurricane proofing in our location.
Did you look at any climate studies about where you'll be in 2050, where the water level will be, or anything like that?
With our selected location, it's pretty far inland, so we wouldn't expect the water levels to affect that too much, but that's definitely something we can look into for the final submission.
Yeah, it'd be probably a good idea just to look at those climate migration maps. I know Florida is fairly low lying, even inland.
Great.
Do you think people in your neighborhood would adopt this if you guys did it? Would it have an impact on the market?
It could. Yeah,
I think it definitely would, especially with the amount of migration down to Florida. A lot of people are spending the money to move down here and investing in areas not only in Live Oak, but where we are in Orlando, Jacksonville, and all across Florida. So these people are energy understand what's going on in our world. So I think this would be they would understand what a great value is to not only be conscious of energy, but to be net zero.
With your current governor?
Thank you very much.
Yes.
Not
It's
sure.
a great presentation. We hope it gets built.
Thank you.
Great job.
We'll go on to the next presentation of Concordia University. They can begin getting ready.
Yes.
Great. Wait, no. There, we have your presentation. And when the jurors are ready, you may begin.
Great. So good morning, everyone. We are the Build for the North team, and we are building engineering students from Concordia University. I'm Maggie.
I'm Hannah.
I'm Kishan.
I'm Yusuf.
And I'm Mihail.
So it was important for us to achieve an annual net zero energy consumption, use material with negative embodied carbon, and allow great importance into cultural consideration. Our project was designed for Iqaluit in Nunavut, which is subject to Arctic climate and very strong wind all year long, which will be beneficial for wind turbines.
Iqaluit currently consists of 60% Inuit, and they make up 90% of social housing. Traditionally, they used igloos and whalebone and hide structures. In the 1950s, they suffered from a high incidence of respiratory disease due to exposure from people from the South. There was a report that concluded that this was due to the poor housing conditions of their traditional architecture. As a result, they implemented housing programs where they imported housing from the South that was inadequate for climate and culture. To illustrate, I'll read a quote. "They put us in a square shack with a big picture window. So there you are. You put up the stove high, everything steams up. The floor is cold as hell and you figure you're quite happy there. The government then figures out you're a family man. So next year they give you a nice looking shack with tar paper walls with white trim and a stove. But there's not enough heat to keep the place thawed out. So in one part of the house you live, one part is cold storage. You've been drawn away from your old ways of living." So currently Iqaluit suffers from a major housing crisis with a lack of housing and many in need of major repair. This includes mold issues, windows that won't close, roofs that have blown off, and houses that have been completely submerged in snow. Another important element of Iqaluit is that it's completely remote without road access. This means everything, including food, has to be shipped up. Shipping containers become a huge waste product, so we've integrated this into the structure of design. We also wanted to foster a sense of togetherness, which is so important to the Inuit community. So these two family units would share the space in the middle. Rather than describing housing program by function, they describe it by temperature. So you have a cold space, which is the entrance, which provides a buffer to outdoor air. The cool space is perfect for traditional habits like sewing hides and preparing meats. And the warm space is the primary lived-in space. We've integrated sliding doors around the interior so it can be completely open, or you can have privacy as required. It's not uncommon for them to all sleep together in a living room and use other spaces for playrooms or workshops. Prefabrication is an important element of our project that allows for a high quality envelope and also addresses some of the socioeconomic challenges that we'll discuss further in market analysis. To further explain our construction process and design elements, we first lay a multi-point foundation frame, then prefabricated floor panels, then the structural components of the shipping container and timber are implemented, and then prefabricated wall and roof panels will be attached to that structure.
Then we'll see how our project offers durability and resilience. The envelope has no condensation risk, which will prevent eventual mold growth. A continuous exterior insulation will be installed to prevent any thermal bridging. And we have included two continuous air barrier in the envelope design as well. A space frame foundation, which acts as a floating slab in case of ground movement, was chosen, as it can accommodate for the permafrost ground and melting due to climate change. One of our goals for the material selection was to achieve a negative embodied carbon. Most of our material are natural and biodegradable, and they're also locally sourced in the greater Montreal area.
To address the past housing concerns and shift away from fossil fuels for environmental sustainability, a hybrid power and HVAC design is proposed. An air source heat pump supplemented by a vegetable oil-fired MCHP provides a uniformly distributed heated floor system. Mechanical ventilation by a dual-core ERV will provide continuous fresh air supply with high recovery, ensuring thermal comfort and indoor air quality. The overall design, powered by renewable energy, can operate in extreme conditions while maintaining a high performance and efficiency with minimal environmental impact.
In Iqaluit, winter is very cold, dry, and windy, which makes comfortable space, heating, and relative humidity a real challenge and a priority. The ERV system helps to achieve required levels by recycling moisture with preheating supply air. Hemp plaster for our interior finish ensures warm, better air quality as a non-toxic element, a perfect thermal mass medium, as well as a great acoustic insulation. The orientation of the building towards south, the roof curves and optimized window-to-wall ratio allows the best increase in solar potential and the heat gain with minimum heat loss. The integration of BIPV system and home wind turbine energy aims to provide renewable sources throughout the year.
With Iqaluit's dependence on fossil fuels for heating and electricity, canola oil is a current ideal Canadian resource for clean renewable fuel. To support local economy, animal wastes and used cooking oils can be collected to be recycled for biodiesel production. The most feasible renewables are wind, solar, and biofuel. Energy simulations demonstrate how the air source heat pump will run all year, while the MCHP will be a backup heat and power generator when outdoor temperatures drop below -4 Fahrenheit. During the peak electrical demand and annual consumption, there is surplus on-site generation, allowing battery storage and sending excess to the grid. A HERS index of 42 was achieved without renewables, but the hybrid design can potentially offer a net zero home solution for Iqaluit.
With only 500 construction workers, Nunavut has a shortage of skilled worker. Prefabricating in Iqaluit will improve the local economy by using the local labor force and reducing external personnel. And with a short summer season, our building can be built in a couple of days, unlike traditional building. Shipping costs are highest for volume, but our envelope is small, therefore lowering the cost, but it still allows for a thick wall with a high R value.
This project is very important because of social factors. Today, Iqaluit has a suicide rate 10 times the Canadian average, as they're forced to choose between living out the traditions of their ancestors or living a modern lifestyle they were forced to conform to. This contradiction in belonging is in part due to the failure of previous housing programs. By listening to the culture and taking into account their traditions and values, a solution to housing can be found, which is what we hope to achieve in this design. Thank you so much for our time, and we'll now take any questions.
Thank you very much. Jurors?
Bravo. What an incredible, great purpose, and you guys did an excellent job.
Thank you.
Thank you. Thanks.
Yeah, I think there's a lot to correct with kind of the pre-assumptions that old housing, failed housing matching had. So yeah, thanks for trying to take this on. Was there a lot of communication back and forth with the community, or how did this partnership come to be, I guess?
Yeah, so we've communicated with a few people, but mostly with experts and extensive research. Because of the design period, we've looked at literary review where they have analyzed what preferences for how they live. Due to the short amount of period, we haven't had time to have feedback on our design, but we wanted to reach out and maybe sort of at the end of our project, get feedback on the finalized design so that we could learn from it going forward.
Great, thanks.
I would encourage you to get feedback now, just because
yeah,
it's just so valuable. Things that you never think of.
We've been in touch with several people who have connections to the community, so we'll reach out to them immediately.
Thank you.
And you had mentioned the 500 construction workers. This is a small community. And the prefabricated panels. So is there, those would be shipping to the site, is that correct?
So currently they are trying to implement or researching starting prefabrication in Iqaluit, which would have a lot of benefits in terms of and the cost effectiveness of our design. So because volume is so, our initial design could be implemented that way as a way of testing the design where it's prefabricated in Montreal. But in order for it to be cost effective, it would need to be prefabricated up there. And so given our wall assembly, you'd essentially just be shipping up 2x3s and plywood and densely packed cellulose. So it creates a very compact shipping. So that's where you'd get the full cost effectiveness. Unlike some of the other common solutions to the climate, which involve structural insulated panels, where you can't it's takes up a lot of space. So a lot of those solutions aren't actually all that optimal given the volume of shipping. But so yes, the idea would be to start prefabrication there, which is already in the process of being researched.
Did you look at geothermal at all? Or I know my brother lives in northern Sweden and they found all this geo wells that were very valuable.
Yeah, so there, I think because of the permafrost, any drilling is quite challenging. I think if there are geothermal, it would be more involved with the ocean. So actually using that as a geothermal source, that could be a solution. And I think people are looking into that. But that might be more at the town level. So it's something, so we've looked more into something that can be implemented specifically for the site and kind of become off grid in a sense.
I love that you're using the excess shipping containers, you know, changing waste into something very valuable, and the waste oil and canola oils, things that are local, and that's so important for long-term sustainability.
Yeah, and a lack of trying to remove some sort of dependence as well, which I think is a struggle there, feeling very dependent. So potentially being able to use your old sources of fueling lamps with whale oil, which is what they used to do, or going